Greetings. Here we have a BK Precision 1655 AC power supply, but I guess they ran out of space here because the official name is that it's an isolated variable AC power supply. So it's a power supply like any other one, but you can adjust the output voltage, except that outputs AC only. So when I picked this up, other than being totally filthy, of course, it had a big sticker over here that somebody made with a label maker, and it said that the meter only shows half of the actual output voltage. And that was it. And obviously they felt that it was a permanent problem, because why else would you go to the trouble of using a label maker to make, with a very large font, write that on here? But I thought I'd have a look. I got it cheaply enough and see if I can make it work. Now, keep in mind, this is not, I have another one. See in the background? You can see this guy, which you've probably seen in previous videos, does the same thing, and it has more bells and whistles. It has 2 meters on it. You can current limit it. So once that's exceeded, it shuts off. But hey, this guy doesn't have as many bells and whistles, but it didn't work properly, so that made it interesting to me. But first off, full disclosure, I've already made the repair, so why am I not showing the video? Because what happened to me was, while filming it, I went out of sync. What does that mean? It simply means that when I thought I was recording, I wasn't, and vice versa. So when I spot checked my video right after the repair, I saw myself mumbling to myself and rearranging the workbench a lot, but none of the real work showed up. But I will walk you through it, and well, that's the best I can do. I did find a manual for it, but unfortunately, and it was available for free from several sources online, but I guess they all get their PDFs from the same place, because the manual I got was missing the schematics in the back. There's still some information inside. They tell you how to calibrate it, and operate it, and they kind of hint at how things work, but a schematic would have been very useful. You can you can buy them, but I'm too cheap for that. And, where's the fun in that? So this way, I actually got to go in and analyze, or had to go in and analyze how this thing was supposed to work to figure out what had gone wrong. But first, let's get into what this thing really does. It's actually quite simple. It's got an isolation transformer, and all an isolation transformer is it isolates the AC line from the rest of the unit, because it's going through a transformer and there's no direct electrical connection between the secondary and the primary, but rather it comes through inductive coupling. And that's something you use, especially if you have like a CRT chassis you're fixing that has a hot chassis or other things. It's a good idea to always use an isolation transformer when repairing something. Now we get to the part where you can adjust the voltage also. So it's got a second transformer in there, which is completely different than the isolation transformer. It's a single winding transformer called an auto transformer, which actually works like a dimmer, like an AC dimmer. You can adjust the voltage by rotating this knob, and that sums up the functionality of it. But then you have a very large analog meter here, and as it turns out, most of the electrical, the circuitry inside of this is used to drive this meter, and it's also got a leakage probe here, where you can test stuff, see if things are leaking. If you're taking your pre-1970s hair dryer and taking a bath with it or something, this would probably detect that you're doing something bad. It's got a solder temperature knob, and all this does is it basically has an output in the back that you plug your soldering iron handle into. And I guess when this was made 30 years ago or whenever, most soldering irons weren't adjustable, but this basically, once you plug the handle into the back, this generates PWM on a triac. So this also kind of performs kind of like what the auto transformer does for the output, in that you can adjust the amount of power coming out of the back of it. But because you're using PWM, obviously what you're doing is you're shortening each of the sine wave periods, and thus your RMS power is less, and thus you are adjusting the temperature of your soldering iron. This is probably not something very useful, but I guess when this came out, they thought it was something really useful. So let's go through a brief explanation of how all of this transformer stuff here is supposed to work, and then we'll look at the repair. So first we have our isolation transformer. Let's do this left to right. And this is the primary winding. And we have AC coming in from the wall attached to the primary. Then we have a secondary. And in this case, the secondary has exactly as many windings as the primary, giving us a turns ratio of 1, which means what goes in comes out the other end. There's no adjustment of voltage done over here, but because we are now inductively coupled, we have introduced a level of safety because we have no direct electrical connection to the AC. And that's all there is to it. It's a 2-winding transformer. It's probably the heaviest part inside of this unit. But then we go out and we hit the auto transformer, the one that lets us adjust the output. And that is a single winding transformer. So it only has a primary. And the way this works is it basically has a number of taps on it. And we have a selector here that taps the output voltage, which is of course from this terminal to the wiper, let's call it. And it's simply, I mean, this is the same principle used when you buy yourself a voltage converter. You're going, say, from 120 volts to 220 to a country that has 240. What you would do is you got 240 coming in here. You know, those things don't have isolation transformers on them. So it puts 240 across the top from here to here. But if the tap is right in the middle of it, then basically we are getting half of the incoming voltage coming out of here. And that's how those little voltage converters that make your electrical doodads work when you have, you know, an old-fashioned power supply that doesn't self-adjust to different voltages. But yeah, it's the same principle. So when you're turning that knob, the big knob on the right side of the instrument, it's moving this and tapping different places and thus changing the output voltage. However, this is virtually continuously variable, and in order to make it, I mean, it's not really continuously, it's still finite, but in order to make it continuous, we're going to need a whole lot of taps over here. Obviously, 4 taps on 120 volts are going to give you, what, 30 volts per tap. So you can go 30, 60, 90, and full blast. And that isn't going to work. So the way these transformers work is that basically, picture this being the windings, and the way these windings are, whereas in the primary transformer, I'm sure you've seen it inside, it's got insulated copper wire. The windings are on top of each other, are touching each other, but because they're insulated, there's no shorts. That it doesn't matter. However, in this case, we have to actually make an electrical connection to somewhere on the primary winding in order to affect the output voltage. So you have to neatly wind the windings on a core and file off the insulation on the part that faces the tap. And as I said, it's still not totally continuous, because you're basically, even depending on how this is built, and I don't know, but even if you're going from one winding to the next, you obviously have a certain step size and voltage there. But if you put enough windings on here, I think the resolution is good enough, as it is in this instrument. And that pretty much tells you what goes on. This is the voltage that comes out the plugs in front, and that is really everything it needs to do to give you an adjustable AC voltage. However, we have the big meter in front, and we need some circuitry to drive that meter. And the way that's done is we tap the output voltage, we have a black box over here, which I'll show you in a minute, and this in turn goes out and drives the meter. And there is a block diagram pretty much of what happens in this unit. So now the complaint was that the output voltage works. I mean, you hook up a meter to the output, and you can see that you have basically variable adjustment of the AC voltage coming out, and you can actually get a little more voltage out of it too. So it's not just so the way the auto transformer works is that you can actually step up the voltage a little bit, and the way you would do that, well, let's not get too deeply into that right now. Let's just assume that we got a voltage range coming out of here. That voltage is tapped, converted to something that drives the analog meter. When I originally took this apart, I had no idea how to open it up. And of course I had removed quite a few of the screws on the underneath of it, and the top still wouldn't come off. Yeah, so the top is now off, with all of the screws on the bottom still in place, as you can see. So live and learn. You just remove a bunch of screws from the back and the top slides out. So here we have what we talked about. Let's see. So in order of what we talked about, we got the stuff coming in through a fuse. Here's the isolation transformer that you can see is pretty large, and all it does is isolate. Here's the auto transformer, and you can see all the neat windings. I mean, it's just the primary, the windings don't cross, but when you turn the knob, the tap on the inside, actually not even on the inside, it's on the outside. See that little arrow thing? That is what changes the voltage coming out of this and being sent directly to the AC jacks on the front of the unit. So now what do we have here? So what do we have here? This is, of course, the meter. And here's the circuitry that drives the meter. So whatever problem there was, and I did verify the problem in that, yes, it was showing, well, it wasn't showing half the actual voltage. It was probably showing about a third of the actual output voltage. So yes, we definitely had a problem in here. Not having a schematic, and if you look at this, there really isn't that much in here. There's 3 calibration pots here, and it describes in the manual how to calibrate this. Assorted passives. There is one transistor over here, but not much else. We have the switches over here. So when repairing it, I figured let's start with the easy stuff and kind of make some guesses about how this is supposed to work. Now, to drive the meter, you're gonna need, for this meter, you're gonna need DC. So basically, you tap the output coming from the auto transformer above, you rectify it, you shape it, and then depending on how the buttons are set in front, you drive the meter with it. Since measuring the output voltage, it showed a seemingly correct output voltage, that means that somewhere in here something's going wrong while trying to translate the AC, the actual AC output, to DC that can accurately drive the meter. So you can see a bunch of diodes over here. That's part of what's rectifying the AC and then shaping it later on. And I just took a meter set to diode check and started checking the diodes. We got the normal looking ones here, the 1N4000 series. And then we had these that looked slightly different. But I unplugged it and I started measuring them, and on a normal silicon diode you expect to see about 0.4 to 0.6 forward voltage drop, which they showed. Then I started measuring these glass diodes, and these first 3, this one, and this one, show the voltage drop of about 250 millivolts. So, of course, when I measured the first one, I went, I found it. But then as I went down the line, I said, well, what are the chances of all 3 of them going bad? I measured the one on top over here, which was the same originally as one of these, and it was open. So it was gone. Okay, great. I found the problem. But what diodes are these? There's no writing on them. And, I had no idea at that point what they could possibly be. But then I put on my thinking cap and basically went, it's telling us what they are. Unless, at that point, the 3 I initially measured were bad, the forward voltage drop was indicating that those are germanium diodes. I still don't know exactly what they are, but from the way it's set up, I can figure out what the max voltage is. Switching speed is probably not an issue. And, germanium diodes are fast, but it really isn't an issue here. So I think as long as I had something that matched the forward voltage drop and had the proper voltage ratings, I should be good. And NTE came to the rescue. I had no idea what exactly to look for, but it turns out that this guy pretty much fit the bill. Found one for a couple of bucks. Didn't have to wait for Amazon or eBay or for things to fall from the sky. And replaced the diode in question, which is right here. Now I tacked it to the top, and that's not clean, I know. Some of you may complain about that, but the problem is if you look at this board as a whole, you see it's got wires coming in from 3 sides. And when I loosened the nuts holding it to the case, I mean, the board wouldn't come out. I had to go in and start desoldering some of these wires to be able to pull the board out and turn it so I could get to the underneath. And since I'm a bit lazy by nature, actually a lot, but I just cut the bad diode out, leaving a bit of the leads in there, and then tack soldered the new one onto the old leads that were sticking out. It is secure, and yeah, you know, I can make it exciting, but yeah, that's what the problem was. Basically, the bridge that was driving the meter, the bridge rectifier that created the DC, had a bad diode in it, and so the meter was showing an erroneous low voltage. So then came time to calibrate it. Remember those 3 pots in there? So we get to the easiest one first, and that is, of course, the actual voltage. Now the first step you have to take before doing anything, making sure it's off, is there's an adjustment in front to null the meter physically. See, you can turn it this way or that, and that was off by quite a bit. Well, now it's being there you go. Okay, so now the meter's nulled with no input on it, of course, and what we need to do now is power it up and basically see what the output is doing. So we turn it on. Now it is on, but you can barely, I mean, this doesn't light up very brightly, but it is on. See? But it's kind of faint. But anyway, so this is kind of set randomly right now. But we can already see, I mean, if we read the meter and we squint a little bit, the meter is actually at about 68 volts. See? So that kind of looks like it got fixed. We need to turn the input voltage to 120 and make sure that it's actually showing 120. So let's turn this. Ooh. Yeah, that's pretty good. And then we look at the meter, and it looks like it's slightly low, so we just stick the screwdriver in here and we look for the one that says voltage calibration. Now, if you don't know what you're doing, don't attempt to do this at home, but simply turning the pot gives us an adjustment range. The pot's pretty much in the middle right now, so I think this is definitely fixed. And here we are at 120, and we can spot check it now. For instance, we can go higher. We can go to 130. Let's see, staring at the analog meter. Yep, does work. And then we can go to the low end. Let's go to 120. Probably a big enough span there. Oh, I didn't even show you that. Okay, let's do this again with the camera showing it. The camera showing the voltmeter. So what we did was we went to 130, and again looking at the analog meter, get it to close to 130 as possible, and that works. And then let's go down a whole bunch. Let's go down to 20 volts. And again, I'm staring at the analog meter because that's basically what you're going to be staring at when you're using this piece of equipment. And yeah, it's pretty close. Showing a little more actually, so it gets a little inaccurate the lower down it goes. But since it's an analog meter anyway, it's very inaccurate. So that one was easy. We got it fixed. The sticker over here that says only shows half the voltage, probably took me like 10 minutes to get off, because when those labels age, they tend to bond to whatever you stuck them to. So it took a while to get that off, but fortunately the video footage got messed up, so you don't have to watch that. But let's set it back to 120. Ooh, we overshot. There you go. So now we got 120, and on we go. Next we need to adjust the amperage settings. And here's the test setup. Looks a lot worse than it is, or not, but it basically starts out with find a 60 ohm 240 watt resistive load. So they're talking about a very large resistor, which, surprise, surprise, I don't have one. But then they go and say parallel light bulbs totaling 240 watts is suitable. Okay, that I may be able to fulfill, except it's parallel, not serial. I was just going to use the dim bulb tester and plug another bulb in here, but that puts them in series. So that's going to increase the resistance there. We want them in parallel. So what I did was, I mean, as far as bulbs, it's not that easy to find, a 240 watt bulb. But what I did find, an incandescent bulb, what I did find is I had two heat lamps that are rated at 125 watts. So we're slightly more. We have a total of 250 watts here, but they're going through this power strip here. So they're in parallel, and they should basically meet the requirements that the meter, that the calibration asks for. So let's see, we got it on the 0 to 4 amp scale right now, which is the upper part of this green scale. And we're supposed to turn it on and increase the voltage till we get 2 amps on here. So let's do that. And it's getting nice and hot. This one's on, and this one's on. And we're drawing about 1.5 amps. So if we crank this up, things get brighter, but we get to 2 amps. Great. But that doesn't mean anything because we have no reference. So see, I cranked it up and it's set to 2 amps right now using the upper green scale. But now we got to insert a meter into the loop to measure the actual current so we can calibrate this. So I could do the stupid thing and try to wire this meter into it with alligator clips and tape and just do dangerous things that would draw the ire of some watchers and tell me that I shouldn't be showing people to do that. And I kind of agree. And then it hit me. I do have a safe solution for this. And here's a safe way to do it. Use my old friend the kilowatt and put it into amps mode. So that'll show me what the actual amperage is that's being drawn. I mean, this is not very highly accurate, but good enough for our purposes. So let's turn it on. I haven't touched the dial, so we should still see 2 amps on the meter, but let's see what those 2 amps are in reality. So this comes on. Oh, it says we have 150 volts running through it, but because I had to turn this thing up to get the meter to deflect to 2 amps. But if we put it into amp mode, we get 2.33 amps. So now what we do is we turn down the voltage till this guy says 2 amps, and then we try to calibrate the meter. So a little bit more. That's close enough, 1.99 amps. Now let's see, since this meter is off quite a bit, let's see if it'll actually let us turn the calibration enough to get the meter up to speed. Down. Nope, we can't. It's turned all the way to one end and it's showing like 1.9 amps. So something in here is a little bit off, but again, for our purposes, it is an analog meter after all. Well, that's the best we can do without me ripping that board apart. It's basically using a 1 ohm precision resistor, tapping the voltage off of that and driving the meter with that. And the thing that could be wrong, or probably is wrong, is that the precision resistor, the precision 1 ohm resistor, is no longer a 1 ohm resistor. So in order to make that absolutely accurate, I would have to find which resistor it is and replace it. And then we can probably adjust it properly. But I'll just put another tag, I'll put another label here and say that the amperage reading is 5% or so lower than what it actually is. And that should probably do it. And it's getting kind of hot in here, which isn't a bad thing. Well, it's turning into a bad thing. It is getting pretty hot, so enough of this. Next we get to the leakage test. Well, the calibration I tried, as outlined in the manual, it was a bit vague and didn't work. I didn't get any meter deflection. However, what I do get is when we get to the performance test, it passes the performance test. So I'm going to assume I did something wrong or my meter blew the current fuse or whatever. But yeah, the performance test basically says reduce voltage to a minimum and connect the leakage probe to the hot side of the isolated output. Of course, what it took me a while to figure out is you actually have to slide this button forward to test. So I'm sitting there trying stuff, nothing's happening, but yeah, you have to turn the probe on. Select the leakage function and slowly increase the AC volts control until meter reads 500 microamps on the leakage scale. The leakage scale's down here, and the green area is basically the leakage current. So we got this thing at 0, we turn it on, and then we go in and what we got to do is, of course, press this button and then turn the dial until we're at 500. Okay, great. Now, what does that mean? Well, they do tell you that this should occur at about 6 volts. So where are we at in voltage? We're very close to 6 volts. So that's the very top scale since I switched to voltage. We're between 6 and 7 volts there, but it said about. So that part seems to be good. And now what we do is increase the AC volts control until the meter reads 5 milliamps on the leakage scale. So we go back here, we press this thing in again, should still be at 500 microns, and now you increase it till we get to 5 milliamps. It's on the lower scale. It's way out of the green area, of course over here, but it's showing 5 milliamps now. So now how do we know that that is correct? And again, it tells us this should occur at about 60 volts. So let's go back to the voltage. Yep, it's at 60 volts. So even though I couldn't go through the calibration procedure, it does seem to work correctly when you're doing the performance test. And finally, you are supposed to check going into, this is basically in the hot leg, and if you go to the neutral leg, go back into leakage, shouldn't show anything, and it doesn't. And then when you select hot on the leakage control, it goes back to the 5 milliamps. Alright, so the leakage meter works, and I guess they don't explain it, but since from 0 to 500 microamps it's in the green range, that means you're okay. But once you're getting outside of that range, you know, the leakage current is too high, and you get something really bad happening in your circuit. Well, she's all buttoned up, and I did some research. Basically, the way you use the leakage probe is you go to the device under test, or whatever it is, you touch a metal part of it, and you have to push. Here's the button that you got to push forward. And if the leakage current is, well, you select leakage, of course. And if the leakage current is less than 500 microamps, you're good. And if it's above 500 microamps, watch out, because something is leaking outside. And I figured last thing, as I was playing around with the meter, I noticed that it has a, which I've never noticed, it has a frequency counter on it. But what better way to test it than to test the line frequency? So I got it plugged into the isolated output and set to frequency. So looks like we are 0.02 hertz off, 0.01 or whatever. Well, looks like that frequency part's working, at least in the lower registers. I could, of course, always hook it up to a function generator and see how high it goes, but hey, that way you know that your line frequency is good. Thanks for watching. Leave a comment and a like, and we'll see you next. We'll see you next time. Oh. Yep, we're still at 120 volts. Oh, let's go back to AC volts. Yeah, it still matches the meter. And now it really is. Bye.